Hi Calculus, this is section 4.7, optimization problems. Optimization problems are when you're trying to maximize or minimize some particular goal. You're trying to find the threshold for what's possible. So like if you're trying to construct a box with a certain amount of material, you want to construct the box. Your goal is to construct the box so that it can hold the maximum amount of material, because there are different ways to construct a box with a given amount of material, and some will hold more volume than others. So that's the type of example we're going to do now, where we have 108 square inches of surface area to make a box. And the box we want to create, we want it to contain the maximum amount of volume it possibly can. So these are examples of boxes that have been made from 108 square inches of surface area. So the box could be sort of flat but wide, or it could be sort of skinny but tall, or it could be anything in the middle. And these were all made with the same amount of surface area. So boxes can be made to hold different volumes with the same amount of surface area. So the goal of what we want to do is figure out what the maximum volume, what's the threshold for 108 square inches. Most students like optimization problems. They like them more than related rates, but maybe you like related rates more, who knows. But most students tend to like these type of problems. When you do an optimization problem, there is usually what we would call a primary equation and a secondary equation. The primary equation is the goal, whatever you're trying to solve, and the secondary equation is you have something that's fixed. You have a particular constraint, like your boss says you only have so much money, or you only have so much material, right? There's something that's fixed. You only have so much fencing, you know, something's fixed in your situation. So let me see if I can draw the box, and you guys know my drawing skills, so let me see how this goes here. Okay, all right, not bad, not bad. I know you guys are thinking not bad either. So now this box has a square base, so that means that the base is a square. So it's x by x by x, and they're not specifying how high the box is, so we'll call that y. So this is a box with a square base. You want to maximize the volume, and the volume of a box is length. The volume of a box is length times width times height. Sorry, I ran out of space here. Times height. Okay, length times width times height. L times W times H. So for our case, the length is x, the width is x, the height is y. So it's x times y, which would be x squared y. So that is the equation for the primary. Now the secondary is our fixed constraint. Our fixed constraint is that we have 108 square inches of surface area. So we have to figure out what the surface area of this is, and this will be our secondary equation. So this box has 4 sides. The sides are x by y. Let me watch what I just said. The box actually has 5 sides. It's open on the top. But in terms of the one that's an XY dimension, you have 4 of them. You have a front, you have a back, you have a left, and you have a right. So the dimension of one of these is XY, but you have 4 of these going around. Front, back, left, right. So you have 4 of those that are the same dimension. The bottom, the area of the bottom is x by x, which is x squared. That's the area of the bottom. Now the box is open, so I'm only going to have 1 of these. If the box was closed, I'd have 2 of those that are of the same area, equivalent areas. So that's the first thing you want to do. You want to figure out what your goal is, write the equation for your goal. You want to figure out what the secondary is, which is your fixed constraint, and then write the equation for that. Once you do that, the next step is to plug the secondary into the primary. So when you look at the secondary, you want to pick the easiest variable to isolate. So as I look at this, the easiest variable to isolate is the y. So I'm going to do that. I'm going to move this over. I'm going to divide off the 4x. And so that is what y is going to be if I isolate the secondary for y. I'm now going to take the secondary and I'm going to plug it into the primary. All right, so here we go. So if v equals x squared y, and y equals to 108 minus x squared over 4x. Okay, I'm going to plug that in for y. So now v is going to be x squared times 108 minus x squared over 4x. So when you do these problems, I want you to think about how can you format this so that the derivative is going to be easy to take. So for me, I don't want to do both the product and the quotient rule. That is going to be too much. So what I'm going to do is I'm going to start by simplifying 1x from the numerator with 1x from the bottom. So I'm going to take away 1x from the top, from the bottom, and 1x from the top. That's going to leave me 1 here. Then I'm going to choose to take this x and distribute it in. I'm going to also pull the 4 out front. You could leave the 4 under the bottom or pull it out front. It doesn't matter. All right, so just to say that again, it was easier for me to pull the 1/4 towards the front and distribute the x in. So this is the easiest place for me to take the derivative. So I'm going to do it here. So, okay, so these aren't related rates, so don't do any DTs. The answer is 1/4 larger. So the derivative of this is 108. Just straight up derivatives like we did towards the middle of class. All right, so I get that. Now I'm going to take out 3. Let's see, 3 into there goes 3, 18, 6 minus x squared. Okay. Now the critical number, remember the critical number is where your highest and lowest point occur. So if I solve this, this looks like 6 plus x, 6 minus x. So my critical numbers here are going to be x equals to plus or minus 6. So I've mathematically done that correct, but in terms of the word problem, -6 doesn't make any sense because these are sides of a box. So that means that the maximum volume is going to occur at +6. I will just prove that to you really quick, not that I'm going to ask you to prove it, but I'm just going to go ahead and prove that with the second derivative test. I just got to watch the time because this can take a long time. All right, I'm just going to prove that's a max with the second derivative test. So I'm going to go back to my derivative here, which I said was 3/4 36 minus x squared. Now if I take the derivative of this, I take the second derivative now. This 36 goes to 0, this goes to -2x, which is going to make this -6x over 4, which is going to make this -3 over 2x. Okay, this is my second derivative. I'm going to now show that, I'm going to now do the second derivative test. So I take my critical number, which is x is 6, I plug it into the second derivative. I'm going to get, it doesn't matter what you get, but I'm going to get -9. -9 is less than 0. For the second derivative test, if the output is less than 0, it means it's concave down. It's concave down, which means that it's going to be, for us, it's actually the max because we have finite material. So let's now answer the question. I've just proved that that's a max using the second derivative test, and now I'm going to answer the question. So the question is, what dimensions will produce a box with maximum volume? All right, so we know that x is going to equal to, what unit are we in here? Square inches. Okay, so x is going to equal to 6 inches. If you go back to the original, when you isolated y, right, we said y was going to equal to 108 minus x squared over 4x, right? Remember we said that? So to solve for y now, you plug in x. So 108 minus 6 squared over 4 times 6. So let's just crunch that out. So it's 108 minus 36 over 24. So what are we going to get here? 72 over 24. And that would go in there 3 times. So y is going to equal to 3 inches. So basically, if the dimensions of this box, we got that x was 6, so this side is 6 inches, this side is 6 inches, and this side is 3 inches. So it's 6 inches by 6 inches by 3 inches. And if you multiply all this together, you're actually going to get the volume. You get the volume of the box. They just want the dimensions, but if they wanted the volume, then you go ahead and multiply that together. Okay, gang, that's the first example. I'll give you some more. I'll catch you soon. Bye.